welcoming Olaf Kolkman.
Oh, I forgot that. Someone has lost a mobile phone. I will put it here up front. If you miss it, come up. You're the only one who can open it and use it, so we trust you.
Yeah, my name is Olaf Kolkman, and I just heard you say we're running on time. As an astronomer, time is one of these things that I think where tinkerers and thinkers met in solving one of the most critical problems. The Royal Society of England had a prize out for establishing time for a long period of time, a precise time, for navigational purposes. That was a problem that took about 100 years to be solved. And that is an area where tinkerers and thinkers come together. I am actually a thinker that became a thinker nerd. How do you say that? Tinkerer. And so, because I'm technically not an engineer, I'm an astronomer from training, as was just mentioned. And I found myself, through hacking and so on and so forth, lost in internet technology. And I'm now at the point where sometimes I call myself an EVE engineer, because I like to talk about the marvels of this beautiful technology. I work for the Internet Society. We're a not-for-profit, and we advocate for a globally connected, secure, and trustworthy Internet for everyone. So that's my background. The talk that I'm about to give is about the Internet and why it's successful. It's not going to be a precise historical talk, but I will look back at the history of the Internet. And there's a few observations there that are my personal observations. I'm not a historian, I'm an astronomer by training, so doing history is not really my forte. When I talk about the Internet, I refer to something that most people in this room might not refer to when they talk about the Internet. I'm not talking about the platforms. I'm talking about the network of networks that provide connectivity to whoever connects to it. To me, the Internet is an enabler for other applications. And the World Wide Web that you use on a daily basis is just an application. Email is just an application. Blockchain is just an application. Some applications, like the World Wide Web, allow other applications to be built on top of them. That's how you create the platforms. That's how you create Twitter, Facebook, Airbnb, Uber, you name it. It's that functionality, those services that actually touch the life of people. And this is not just a stock photo. This person is Yazgul, and her last name is Tini Bekova. She's 36 years old, and she's an ICT teacher in the mountains, the Tian Shan Mountains in Kyrgyzstan. Her life was changed when her school was connected. That enabled her to teach her kids better. Internet continues to impact the life of people. I think that the reason why Internet became this globally dominant system, communication system, is the result of a few brilliant insights, a culture of openness, and aligned developments. I think there are two factors to that. The brilliant insight, I think, is the invention of packet switching. And then that second factor is open technology development. And I'll dive into them a little bit more. But first, for fun and a little bit of hyperbole. This is more than 100 years ago, late 19th century. About 2 decades before this institute got created. 1893. Sweden, at that time, was the world leading country in this new communication technology called telephony. This country had the highest density of connected people. There were 4 telephones per 100 people in Stockholm. There was half a telephone per 100 people in the whole country. You were very advanced at the time. The telephone network was special. It was a network that was built for one application, well, two applications. Telegraphy and telephone. And it did that well. And the way that it was built was by circuits, by using wires to connect terminals to each other. And the way that you connected the wires were through patch panels. By the way, one of these jobs that female workers gave jobs to female workers in technology. The technology design, the architecture was very vertical. It was tightly integrated. The telephone handset, the network itself, the electrical properties, everything was very, very tightly integrated. And it allowed the network to do that thing, what it did well, very good, namely voice telephony. And it allowed to charge for those calls, because the telephone networks needed to run. Packet switching is the thing that I think allowed that application and the network to decouple from itself. So, in contrast to circuit switch networking, packet switch networking allows the utilization of one circuit, one line, one connection by many, many parties. That realization came from statistical analysis that was done in the early 19th century, or early 20th century, and it led to an idea championed by Leonard Kleinrock to chop off information in chunks and create small little buffers in which you could store the chunk and then just wait for free space on the wire to put the information on. When you hear me talk, you notice silences. We're not using this communication channel very effectively. There's too much silence on it. We could have two talks. Somebody else using the silences in my talk to have another talk. That's how packet switching works. You use the silences on the wire to put information. And by doing that effectively, you create a use of the network very effectively. Obviously, this was done in a situation where in networks where you had very expensive computers that needed to be time-shifted. So this is in the ARPANET, mid-60s or late 60s and early 70s when this was all invented. In the ARPANET, they used packet switch networking, and they invented the first applications like email. Email was invented in 1972, and at that same moment, roughly that same time, people started to realize that the ARPANET is probably not the only network. There are other networks that are built too, in the US, in Europe, everywhere people were building networks to connect computers together. Now, how would you connect the networks to other networks? How do you create a network of networks? This is when Vince Cerf and Bob Kahn came to the stage. And they proposed the ideas that eventually came to TCP/IP, which is the names for the protocols on which the current day internet still runs. With TCP/IP, it became possible to connect almost any network to another network, and thereby allowing inter-networking to emerge. It was all based on a few architectural principles defined by Bob Kahn. Each network would need to stand on its own, and no internal changes would be required to any such network to connect to the internet. No internal changes to any network. Packet forwarding would be on a best effort basis. If a packet didn't make it to the final destination, it would be retransmitted. That's a profound realization. You can lose things. You don't have to have 9 nines. Black boxes are used to connect networks together. They're now called routers. And and gateways. There is no way for these gateways to keep state of flows going through them. They act on a packet per packet basis. They are kept simple and they're kept neutral. That avoids complicated adaptations into the networks when new applications are being made. And it allowed for easy recovery of failure modes. So very simple architectural properties allowed for cheap devices to be built. Finally, no control globally, no global control at the operational level. In the internet, there is no Tsar that controls it. And those simple principles are still applicable, be it as an ideal, in the internet today. The internet of today is a network of independent networks that voluntarily exchange IP packets. They do so from end to end. Moreover, there's a reasonable amount of redundancy which allows the network to be resilient for failures, which means you can use relatively simple equipment. Equipment that is not designed to be 5 nines. 5 nines being 99.999% uptime. 5 minutes downtime per year. You don't need that type of equipment. A router can fail, and packets will find their way across the internet in different ways. More importantly, from the application perspective, from the things that are built on top of the internet is an abstraction. The network itself is an abstraction. Applications just count on the best effort basis of this packet routing. And from the network perspective, applications just produce packets. Also, applications are an abstraction. And there's an explicit agreement because of all of this where the complexity is managed, namely in the endpoint. That is where you decide whether you want to retransmit a packet because the other side says, I don't have all the information that I need from you. It's the endpoints being that mobile phone that was just laying here that now has magically disappeared. Somebody must have picked it up. Those endpoints make the decisions whether retransmission of a packet happens. Isn't that fascinating that all the devices that we have in the room, and I see a few hundred people, so there must be 1,000 devices here, all make individual decisions about retransmission and make the internet work. We often express this abstraction in a layered architecture. Some of you might have heard of OSI layer. It's all abstractions. But the beauty is there's no Tsar that determines all how this works. These type of things, the applications and the networks, can make their own decisions. And if you look at networks, this is a network of networks, and no networks need to make a globally set of bilateral agreements in order to get traffic from Sweden to Uganda. My friend Patrick here has a network. He only talks to his networks and his upstream pays a little bit of money. That upstream pays a little bit of money to another upstream. And traffic gets routed on best effort and makes it there. There's a global collaboration going on to make this happen, a global set of norms, a global understanding that delivering packets creates the connectivity which creates the value. The only thing that you need to coordinate globally are unique addresses and the naming of devices. And you do that with a global hierarchy. That's quite amazing. So, packet networking. Another thing that I think was quite important for the onset of the internet was open technology development. The previous speaker already talked a lot about openness. And so I'm happy to see this repeated here. openness is really, I think, the key, the spirit of openness, of sharing, is really the key to how the internet grew. The people who were experimenting in the ARPANET in those early years created that culture of openness. In fact, they started a documentation series, which are called Requests for Commons. And what I have is here a picture of RC3. And RC3 basically describes the purpose of the series. So this is from April '69, Steve Crocker. Notes are encouraged to be timely rather than polished. Philosophical positions without examples or other specifics, specific suggestions or implementation techniques without introductory or background explication, and explicit questions without any attempt to answer are all acceptable. The minimum length for a note is 1 sentence. These standards, or lack of them, are stated explicitly for 2 reasons. First, there is a tendency to view a written statement as ipso facto authoritative, and we hope to promote the exchange and discussion of considerably less than authoritative ideas. Second, there is a natural hesitancy to publish something unpublished, and we hope to ease this inhibition. That is the birth of the internet. That spirit, that mindset, open exchange of ideas. That is the birth of the internet. The RC series and that mindset sort of evolved. Currently we have the Internet Engineering Task Force, which is a global standards organization, a very open forum in which any engineer can participate without even paying a membership due. All the work takes place on mailing lists. That spirit is still there. Internet drafts are published, they are reviewed, they are commented on mailing lists, discussion happens. And sometimes these drafts and ideas get promoted to a specification that is interoperable and is called standard. We're now at RFC 8,500 or something thereabout. Now, the early internet was not the only open system that was evolving in a similar way, in that way. And there were other systems. At the same time that the internet was evolving and becoming a more widespread infrastructure, there's the rise of open computing systems. Unix came to the surface. And the beauty of Unix was that it allowed an open specification of its APIs. The implementations were still proprietary at that time, but the APIs, the application programming interfaces, the thing that you needed to talk to in order to create a program on top of that system, were all open. So if you created a program, you were basically, that was independent of the hardware of which the Unix operating system worked. And if other hardware was developed, and that happened quite often in those times, then the Unix system as such was ported, and you could create all your applications again very simply. It's that same idea of splitting the network from the application happened in computing as well. Separating the hardware from the application by creating essentially layers. So that also allowed the birth of open source software. The Unix operating system was an AT&T system, it was proprietary, and Berkeley did quite a lot of work, the University of Berkeley did quite a lot of work, and at some point they had implemented the TCP/IP stack. And since Berkeley was a publicly funded, federally funded institution, all the results of their work were supposed to be open. So the network stack, the TCP/IP network stack in Unix was published as an open specification, as an open source package that everybody could use and build on. And it's that piece of software that allowed Windows to start using TCP/IP and other systems to start using TCP/IP. And the evolution of these systems took off in the 80s. I think the internet being a critical part, and that sort of set the stage of the digital societies. While the computers were growing, Moore's law, you know, the circuits get more dense and cheaper every, whatever, the price the capacity doubles for the same price every 2 years or something. That's Moore's law. So computing gets cheaper, we start to digitize our environment. We start to scan our documents, we start to record our voices, we start to record our music, our videos, and so on and so forth. And as the price of computing rises and the capacity grows, we can do this more efficiently. And at the same time, the internet develops. So we can share these things. We can share our ideas. We can share our videos and our movies. This is when cat videos are boring people. But mind you, the network was not designed to do cat videos. It was designed to deliver packets. And Moore's law sort of, you know, allowed these two things to evolve hand in hand. But we didn't need to make changes to the internet because suddenly somebody decided that cat videos were a thing. And still the complexity is managed at the endpoint. I guess you all noticed this. You know, you're in the house, at least I noticed this. I'm in the house watching a Netflix movie, and suddenly my son tries to play a game. You know, I get some degradation of quality of the series. There's some packet loss, perhaps in the network, but the network deals with this. There's this unspoken rule in the internet, this collaboration rule that you treat each other sort of fairly and honestly. This property that applications do not need to negotiate with the network is very important. It allows for permissionless innovation. I will return to that. I also think that the internet allowed itself to grow. This is the tinkering that the first speaker talked about. First RFCs were stenciled and distributed by mail, and later we distributed RFCs on the network itself. And it allowed people to understand the technology. It allowed people to tinker with the stuff. This is exactly how I entered the industry. I was studying astronomy. I needed stuff to work to do my data analysis. I went on the internet and fixed something. This is how I got interested in internet and internet engineering. And still today, the flywheel of innovation is people coming together. Hackathons, it's GitHub, it's Stack Exchange, and if you don't know what that is, Google for it. Permissionless innovation, I just mentioned it. That is, I think, key to the internet exchange, internet success. The fact that if you build an application, you do not have to negotiate with the network. You build the application. When Tim Berners-Lee invented the World Wide Web, he did not need to negotiate with Vint Cerf, the inventor of the internet. The World Wide Web itself is arguably the most successful application of the internet. The World Wide Web itself has the same generative properties as the internet. You can innovate on top of the World Wide Web protocol, HTTP, and create services out of that. Permissionless innovation, yet again. It's the open specifications and the interfaces that offered the reusable building blocks that allowed our system to evolve. At the Internet Society, we say that permissionless innovation is what we call an internet invariant. That is a property that is not necessarily invariant, but a property that if we lose it, the internet is not the internet anymore. We can have global networks, but at the moment you have to negotiate with the owners of the network that you want to build an application, we don't have the internet anymore. We have a closed system that will produce telephones, because the network and the applications are tightly linked, and innovations will become less possible. Other internet invariants, so things that I think are core properties of the internet, and that we can lose if we are not careful, are the global reach and the integrity. If something is entered on the internet at one side, it comes out at the other side of the internet the same way. Nobody touches what is in the middle, ideally. It's general purpose. It's not tailored to very specific applications. It's accessible. Everybody can connect. If I want to build a new network and become part of the network of networks, I can do so. That happens on a daily basis. That lady in Kyrgyzstan was connected because somebody decided to build a network and connect it to the internet. Accessible and extendable. And it uses reusable building blocks. Sort of a layered approach. You have building blocks that you can apply in all these vertical types of applications that people are building across the world. But the internet interacts with society. Most of the discussions that we see today is how internet makes us interact with our digitized environment. The internet and the digitization of our world has had enormous positive impacts. We talked about positive impacts before in this room. But at the same time, we worry. We worry how the data behemoth, Googles, the Facebooks, the Twitters, the Amazons, influence the very fabric of our society. We worry about our privacy. We worry about the fact that police may not be able to gather incriminating evidence because we encrypt our communication. We worry that cyber criminals can get to our assets, and yes, they do. We worry that some of the platforms that we are used to have the economic power that is larger than a small country. Those are all very valid things to think about. And when we address those worries, we often have to realize that those are not new problems. They are old societal problems that have a new life and are different because of the size and the speed that digitization and interconnectivity has offered. And when we try to solve those problems, then I think we engineers, have a role to play. We are responsible for building these very complex systems that often, and I would say, in the case of the internet, I myself do not fully understand. We understand the pieces, we understand the building blocks, but we don't quite understand as a society how those building blocks interact together and create circumstances for consolidation, or when certain destabilizing activities might happen. But we as engineers have a role to provide that understanding, to be in the room when decisions about societal aspects are made. We can help to appreciate those most wicked problems in society. And we have some approaches for that. When we design things, we have to make sure that we understand the societal circumstances in which our solutions might be deployed. If there is a societal choice to make, then perhaps we should design for that choice. We should design for the tussle to work out. Dave Clark has a paper, the Design for the Tussle. very worth reading. It basically says, if you design technology into the society, make sure that the society has some parameters to choose. Some people may say there are easy problems to the problems that we face. And by introducing those easy problems, we might face other problems, side effects. We might lose those invariants, those properties that make the internet the internet. And I believe that we as engineers should be there to inform policymakers and others what they tend to lose if they go for certain solutions. We have to inform them about alternatives. At the Internet Society, we believe strongly that addressing societal challenges need all parties all around the table. Governments that are responsible, among other things, maintaining public safety and looking out for consumer welfare. Private sector, because they operate so much of the internet. Civil society as a voice for the rights of users. And us, the technical community. The technical community that brings understanding of the systematic nature of the thing that we're looking at, without necessarily bringing a specific business interest. We call this the multi-stakeholder approach. And I think that allows us to find solutions to very wicked problems. And those solutions lie in smart engineering, smart regulation, or smart business practices. And I think I'm preaching to the choir, because I think that the Ingenieurswetenschapsacademie, or Ingenieurswetenschapsacademie, as we say in Dutch, has been founded around these principles. It's the multi-stakeholder principles and processes that allow different experts to learn from each other and allow for creative and